Okay, so welcome everyone. So today we have two probability talks in the morning. So it's my pleasure to introduce Shirshendu Ganguly from University of California, Berkeley. He will talk about recent progress in the study of Gibbs measures on line ensembles.
Yeah, thanks a lot for the, am I audible? I think I'm, okay, thanks a lot for the invitation and thanks to the organizers for organizing this beautiful conference. This is my first time at ISR Pune and I'm sort of quite impressed by the campus. And okay, so the plan for today is to sort of give an overview talk on some recent developments on line ensembles or random curves. And I'll talk about some of my recent results, but as well as sort of give a broad overview of some of the other developments in this area. And I'll primarily focus on a bunch of examples. So and we'll sort of go back and forth between different models, and we'll see. So okay, so to get started, so just generally, what is sort of the context? So line ensembles are a family of random curves that occur in many natural contexts, as we will see. And typically, these curves will be interacting under some sort of potential, and they can depend on the exact context. But overall, sort of the kind of models that we'll sort of encounter will have a sort of a common theme that we'll sort of soon see what it is. Okay, so what kind of examples we will primarily focus on? They will primarily arise from height functions in random growth processes, a particular instance being the polynuclear growth. Again, I'll make all of these things more precise. Eigenvalue processes are random matrices. And the other example that we will sort of spend some time talking about will arise from level lines in lattice surface models. In particular, much of the motivation will come from understanding the three-dimensional Ising model. And again, as I said, like the object of interest are a bunch of random curves, and they will be actually typically ordered. So there's going to be a top curve, there's going to be a second curve, and often in applications, the top line turns out to be the most important. But thinking about them as a whole ensemble of curves can be quite useful, as you will see. Okay, so to get started with the first example, so Dyson-Brownian motion, and this is the eigenvalue process that I alluded to in the previous slide. So take an n by n matrix, which is Hermitian, and up to that Hermitianness, let's say the entries are IID complex Brownian motions. Okay, so these are all standard IID Brownian motions with a real part and an imaginary part, which are themselves like independent Brownian motions, and it's sort of Hermitian. So that's the constraint, and so the Brownian motions are evolving in time. So for each time slice, I have a matrix, and so I can write down their eigenvalues. And let's say I ordered them. So let's say this is a Hermitian matrix. So these are real eigenvalues. And so let's say lambda1 through lambda n are the eigenvalues. And I look at their process, look at that process of n particles. Is there a question? No. So there are n particles and they're evolving across time. And so this is what is sort of alluded to here. So initially all the Brownian motions start from 0. So the matrix is a 0 matrix. So all the n eigenvalues are 0. And then eventually they will start growing, and it's not too hard to convince yourself. So this is how it might look, right? So I'm like, for any given time point, it's just a Gaussian, it's just a standard Gaussian matrix because Brownian motion at any given time has a Gaussian marginal. So for any time slice, these are just the eigenvalues of a unitary Gaussian matrix, and people know what the growth rate of those eigenvalues are, and because of diffusive scaling of Brownian motion, essentially at time t. The top curve is going to be at location square root t times square root n plus some correction, okay? And similarly by symmetry, the bottom curve is going to be roughly, I mean, at minus root t times square root n, okay? And it turns out, which might not be completely obvious, and it's a sort of non-trivial fact, that this process of eigenvalues, which encode eigenvalues of matrices, entries themselves are Brownian motions, themselves turn out to be also Brownian motions, except the constraint that now the eigenvalues are ordered, so the Brownian motions have to be ordered. So this is sort of the basic point which allows one to study this using properties of Brownian motion. So the trajectory of n eigenvalues themselves are like n Brownian motions conditioned to not intersect. And this description leads to both probabilistic and algebraic properties that will be crucial in its study. Okay, so this is one system of random curves that will feature again and again. So just keep this in mind. So n Brownian motions non-intersecting, or you can think of also like n random walks non-intersecting. And again, as you will see, so this is going to be a key object in this story. Okay, so the other class of curves that we will sort of look at, and these are not unconnected, will arise from models of growth, and this has been a feature of some of the earlier talks. So for some last passage percolation, again, I won't be super precise about the definition, but these are models of random geometry or random metrics or antimetrics if you look at the last passage version, where you take, let's say, the usual Z2 lattice with its graph metric, but now let's say you distort it using random noise. Okay, and the noise is, let's say, IID, and this is going to be a metric ball. So I'll be a bit more precise in the next slide. So here is a sort of general setup. So you have the usual Z2 grid, and let's say you put random weights on each of the vertices. You can put them also on the edges, but like we'll not be very focused on the precise details of the model. And then between any 2 points, you can look at any path, and you can just sum of the weights of the vertices along the path. And you can try to minimize them if you're in the first passage setting. You can try to maximize them if you're just restricting to oriented paths in the last passage setting. These extremal paths will be called geodesics. And how does one get a curve out of this? One way to do that is, let's say you take a hyperplane, and let's take the origin. Let's say this point is the origin, and you take this hyperplane. And let's say as the point X moves on this hyperplane, you trace out the distance from this point to this point. Okay, so that gives you a function in some sense. And that's roughly going to be the top curve in the ensemble that will arise out of this example. Okay. As I said, so there's a natural growth interpretation of these models by considering the metric ball. So as you're looking at larger and larger radii, the balls are growing, and that sort of models random growth. And a particularly elegant description of this growth happens when the weights are exponential random variables, and you're looking at last passage percolation. So this also goes via the name of corner growth model. And again, like quickly, what it does is basically now you, let's say, rotate Z2 to look at this positive quadrant, but rotated by 45 degrees. And let's say you start from just this wedge, and every time you have a corner that is unoccupied, you fill it up at rate 1. So the corners keep getting filled up. And it's not too hard to see. So this fact that it's getting filled up at rate 1 is where the exponential variables come from. And so there is a coupling of this last passage model and this corner growth model, as I've stated here, so that if you take any cube and you look at the time at which this gets filled into the cluster, is exactly going to be the last passage time from this point to this point. Okay, so this is how the corner growth model sort of encodes the underlying last passage problem, a last passage percolation model. And okay, so I said what the top curve is. The top curve is the distance profile to any hyperplane. And it turns out that you can go further with this and get multiple curves. And again, I'll just give you the description of how to get these curves, but not quite sure why the curves are ordered and so on. So it turns out that you can actually embed the top curve, let's call that to be L1x, in a family of curves L1x bigger than equal to L2x, blah, blah, blah. So how do you get those bottom curves? So previously I took a point, the origin, and took a point X on this hyperplane and measured the distance from 0 to X, right? That was the top curve. Now, instead of looking at just a single path, now you can look at multiple paths starting from the origin and going to X, so that they're all disjoint except, let's say, the first and the last point. And you can look at this ensemble of paths here that maximize the total weight. Okay, so if you have a single path, then you just add the weights along the path, and you're looking at the path that maximizes the weight, which is the geodesic. Here in this at-least diagram, you have 4 paths that are disjoint, and they are, let's say, cumulatively maximizing the total weight. Okay. So for every number from 1 through, let's say, n, if n is the size of the system, you can define those geodesic watermelon weights, where the top path corresponds to the geodesic weight. The second curve is defined by this relation. So if you look at the sum of the top 2 curves, they will give you this maximum weight of 2 disjoint paths. If you look at the sum of the top 3 curves, that will give you the maximum weight obtained by having 3 disjoint paths between 0 and X. And again, as X varies, this gives you a family of curves for each J. And that's a line ensemble that you get from this picture. And it turns out that this is sort of encoded through this RSK bijection, which I'll not go into. But so this is the distance profile, the top curve. L1 plus L2 is the maximum weight of 2 decision paths, and so on. Okay. As we will see, this example is not unrelated to Dyson-Brownian motion. Wilson's, yeah.
How many allies you have depends on your X.
Not X, but like, so there, I'm like, okay, so it depends a little bit on the system size. So suppose you have an n by n box, then you can only get n paths, because otherwise you will not have n decision paths. Yeah. But like, so in this LPP setting, we are looking at like, okay, I sort of rotated things, but let's say you're looking at oriented paths. And so if you're just doing along the x-axis, there are not too many oriented paths. So the right direction to do that is in the 45-degree direction. And now let's take the endpoint to vary on the top line or something. Yeah, but generally, if the system size is n, then you will get n paths. And in some of the limit, there will be infinitely many paths. Yeah, it's the first point is always the origin. Yes, that's L1 plus L2. So L1 is fixed because I'm looking at the best path. That gives me L1x. And then I look at the best two paths, that's some number. That minus L1 is L2x. Yeah, so so exactly. So L1 plus L2 is the answer to the maximization problem with two paths. And similarly for any J. Okay. And another model is polynuclear growth. Again, I don't want to be super, just more stuff to get into, but here quickly, this is another example of a random growth where, let's say, particles rain at rate 1 on the substrate, and whenever particles land somewhere, it then starts expanding at rate 1 on the two sides. Okay, and so this gives you some, so for every point, you can look at the height of this interface at that point, and that's going to be some curve. And this is actually nothing but last passage percolation in a Poissonian environment in this guys. So this is sort of goes back to work of Prohofer and Spahn. And again, like this is again going to be the top line, and there are ways to extend this definition to multiple lines. Okay, and as I said, the DBM is not quite unrelated to LPP. So it turns out, and this is a remarkable equality distribution, that, okay, so far in the LPP model, I said you take Z2 and then you add IID weights and then you look at maximizing weights. But instead of doing Z2, you can sort of think about a sort of semi-discrete version where Z2 is replaced by these copies of the real line. And now instead of IID weights on the vertices of Z2, you have this IID copies of Brownian motion. And this is in some sense a semi-discrete limit of the Z2 picture. And again, you can define last passage percolation problem in this environment where paths are now oriented, which means you spend some time on the bottom layer, then jump to the next layer, then jump to the next layer, and so on. And then for any such blue path, you look at the energy of the path, which in the discrete case was some of the vortex weights along the path, now becomes the sum of the Brownian increments along this path. Okay. And so it turns out that as X now varies, this becomes, so suppose there are T levels here, then as X varies, this exactly becomes a Dyson-Brownian motion with T many eigenvalues. So it's a T Dyson-Brownian motion. So, and this is a completely non-trivial connection between LPP and Dyson-Brownian motion. And okay, so, okay, and one more model in this regard that I want to point out is a positive temperature version of things. So far we were looking at paths that maximize or minimize their length. But in place of that, you can also pretend that you put a measure on all paths. So for any path gamma, you can put a probability measure whose density, let's say, is proportional to e power beta, where beta is some parameter that you can think of as inverse temperature times the length of gamma, right? And so now instead of having a single path, which is geodesic, now you have a probability measure on paths. And if beta were somehow infinity, this probability measure would degenerate to the path that has a maximum length. But this is a softer version of that where you are putting non-trivial probability on every path. And then Z is the corresponding partition function that you have to divide this thing by to make it into a probability measure. And the corresponding geodesic length is replaced by a log of the partition function, right? Because you see that if beta were infinity, this thing would essentially be coming from the single path which has the maximum length. So if you take the log of that, you would essentially get the geodesic length. So in the zero temperature limit, this quantity fxt is exactly the geodesic length between 0 and x comma t. Right? So this is in some sense a softer version of the LPP problem. And when the underlying noise is, again, so this model obviously makes sense on all of these discrete models that I've talked about, but in particular, when the underlying noise is Brownian, this goes by the name of O'Connell-Ure polymer. So somehow the geodesic is thought to be as a zero temperature polymer, which is extremal polymer. Okay, so far we talked about a few examples which came from eigenvalues and last passage percolation models. And the next examples will arise from the Ising model. Okay, so again, so at a high level, what they will be is our interfaces separating phases in the Ising model. And what does that mean? What does that mean? So just to sort of recall that the Ising model is a measure on spin configurations. Again, you can make sense of that on any graph, but for us, it's going to be Z2 or Z3. So you have some, let's say, n by n box, and you're assigning vortices spins which are either +1 or -1. And the probability of a particular spin configuration is going to be proportional to exponential of beta, again, an inverse temperature parameter, times the number of agreements. So in some sense, if beta is very high or the temperature is super low, you're forcing the measure to concentrate on configurations that have very few disagreements. Whereas if beta were close to 0 or the temperature was super high, the particles are behaving somewhat independently and they have no connection to each other. Okay, so that's sort of broadly the model, and it turns out that this model has a phase transition. So in low temperature, so there is a critical temperature below which you expect this long range order where particles will tend to typically have the same spin in the neighborhood of each other. And so in this particular context, when you have a low temperature Ising model, you can look at different boundary conditions. So in this picture, you have an n by n box, and let's now fix the boundary conditions to be plus, plus, plus on the top 3 sides and minus on the bottom side. Okay. So, but recall that we are in a low temperature setting. So particles close to each other will tend to have similar signs. And because it's low temperature, the boundary has some non-trivial effect. Now, things that are close to the plus boundary will tend to be plus, and things that are close to the minus boundary will tend to be minus. Okay, so this gives you an interface which separates the predominantly minus phase close to the bottom to the predominantly plus phase, which is in the bulk of the box. Okay, so is the broad setup clear? So you see that you're naturally getting some sort of a curve which separates these two phases. And so it's known that if you have an n by n box, this interface scales like square root n, and if you scale it by square root n, it converges to a Brownian excursion. And so which means that the fact that this bottom floor was all minus pushes this curve up. Recall that Brownian excursion between 0 and let's say 1 does not hit the value 0. It's strictly above 0. So somehow the effect, this is because it's actually much more costly for the curve to stay non-negative, but yet be close to 0 all the time. So somehow the fact, so entropic considerations force this curve up. Forces, yeah. However, an interesting phenomena arises if you now also add a positive field. So what is a positive field? I did not write that in the model before, but so essentially, instead of the model just being this, where you are looking at the number of disagreements, you're, let's say, also adding a bias where every vortex is likely to be slightly more likely to be plus than a minus because of the addition of the positive field. Okay, so here there is this measure is symmetric in plus and minus, right? So if all the sigmas, if for any sigma, if you flip the signs of every vortex, the measure does not change because you're just measuring disagreements. But if you add a plus field, then it breaks the symmetry and it tends to make vortices more close to plus. Okay, just to write down if people are not familiar. So essentially the model is the following. Can people at the back see? Yeah, so this is the term that we already have. Right, this is the term that we have, which is a symmetric term. It does not depend on whether we're looking at sigma or minus sigma. But now you add, let's say, a field lambda plus. So lambda is the strength of the field, which means that because lambda is positive here, your sigmas being plus biases the measure more. Okay, so this is the way you can break symmetry. I guess we can turn off the lights now. Sorry. Okay, so what is the effect of a field? You see that this is predominantly minus and this is plus, but now if you add a positive field, it will tend to make more vortices plus, right? That's the effect of a positive field. So it will push this interface down. So it's going to try to decrease the region of minuses, right? Because it's going to make more and more vortices tend to be tending towards plus sign. So this thing without a field is like a Brownian excursion. But if you add a field, it faces a downward push, right? So there is entropic repulsion that is pushing it away from the floor. And there is a field which is giving it a downward push. So that gives you some competition. So there is force in both directions. Yeah, so in particular, this is a cartoon of what you might expect to happen. So if this is, let's say, the lambda 0 case, which is just a Brownian excursion type object, as lambda increases, it becomes more and more closer. I mean, it pushes the curve more and more close to the bottom floor, right? Okay, so let's sort of, that was a discrete model. So you can try to see what would be a continuum scaling limit candidate for this. So we said like this thing is supposedly like a Brownian excursion in absence of a field. And you see the effect of this field. Okay, let me use the pointer here as well. So effect of this field is, so this is in some sense getting like the larger the negative area is, the heavier the penalty is for this measure, right? So somehow that, if you think about it, is manifested in this model in this following way. So the candidate scaling limit would be something like a Brownian excursion, but now tilted by a factor which is like e power minus lambda times the area under the Brownian excursion. So the larger the area is, the costlier it is for that curve. So which means that the optimal thing would be where a trade-off between Brownian fluctuations and this negative force is sort of balanced out. Is that intuition roughly clear? Again, so the model of the story is the effect of the field is manifested in this e power area tilt. So the larger the area is, the costlier it is. It is favoring curves which have smaller area under it. Okay. And again, as we will see, this is sort of a pretty crucial building block in many of the forthcoming discussion. And the final class of curves we will discuss arise from a 2 + 1 dimensional height functions. So some canonical examples include, let's say, lozenge tilings of different domains, integer Gaussian free field, and interfaces in low temperature but 3D Ising model. And this is the one that we will mostly focus on. So this example that we just talked about was in the 2D case, where you had just one curve separating the plus phase and the minus phase. When you're looking at a 3-dimensional situation, it will turn out that there will be multiple curves, which will take us into the realm of this line ensemble picture. So just to give a sense of, I mean, like this is a model that we will not discuss, but just to give a sense of how you can expect line ensembles to arise from height functions. So this is a tiling of this domain using 3 kinds of lozenges. As you can see, there are 3 different types of lozenges, and that naturally leads you to encoding this filling up as a height function, right, in the way that is denoted here. And you can also sort of now look at the level curve. So these cubes are all at height 1. These cubes are at height 2. So you're getting, like, for all different levels, you're getting some curve. And because so just by looking at a random height function and looking at its level curves, you get a bunch of curves out of it which are non-intersecting and get a line ensemble. Okay, so this particular model is the lozenge tiling of this hexagonal domain, and but our focus will be a similar story but in the Ising setting. Okay, again, so let's say 3-dimensional Ising model, again with a, so now this is like an n by n by n box in 3 dimensions. And now let's say I again do a thing where I have all the boundaries on the top half are set to be plus, and all the boundaries in the bottom half are set to be minus. And again, we are looking at a low temperature situation, which will give me some interface separating the 2 phases. Now, obviously, one has to be a bit careful about what an interface means because there are some discrete annoyances, and you can make sense of that by looking at star-connected components. But we'll sort of, for the moment, not worry too much about those microscopic geometrical details, because we will eventually work with things like Brownian motions and whatnot, which are supposed to be the continuum scaling limit. Okay, so unlike in 2D, and this was sort of one of the famous constructions of Dobrushin. So in 2D, remember that in absence of a field, there was an interface, but that had a Brownian fluctuation. So as the size of the box grew, the fluctuation of the interface also grew, right? So it was fluctuating like square root n. However, in 3 dimensions, it turns out that whatever the interface is between these two phases becomes rigid. So their fluctuation is order 1. And this allowed Dobrushin to construct non-trivial Gibbs measures in which were not translation invariant in 3 dimensions. So the main point is the surface or separating the two phases has order 1 fluctuation in 3 dimensions. So which means that if you look at the interface, that's mostly going to be near this half plane, separating the top and the bottom halves, and it's only going to have like order 1 fluctuations away from this plane. Okay, that's a typical picture. Okay. However, now let's add a hard floor. So recall that in this figure, the boundary conditions, so the separating hyperplane had some distance from the boundary conditions on both sides. So there was a top half and there was a bottom half, and then there was an interface in the middle. But what if you push this floor from here to actually at the half plane level, which is going to give you a hard floor, right? So now the interface. So can you see the distinction between this boundary condition and the previous boundary condition? So now there's a cube, and only the bottom surfaces. Actually, okay. So this figure is wrongly drawn, but so this bottom face is the only one that is blue. So you have an n by n box, but only the floor is minus, and every other boundary is plus, which is exactly the analogous picture from the 2-dimensional case that we looked at. And so now again, there's going to be an interface, but has a hard constraint that it cannot go below this bottom floor. So which will have the effect similar to what we had for the Brownian excursion, that if you have a floor that you cannot go below, from entropic considerations, it's much more optimal for the surface to rise up than stay consistently near the floor. For 2 dimensions, this height that it rose up by was like square root n, because it was like a Brownian excursion. Here, in absence of a floor, the typical fluctuation was order 1. But if you add the floor, everything rises up to a height which is like logarithmic in the system size. Okay, so this will raise the interface between the two phases to a height which is like log n. So now you see that the interface, which obviously starts from 0 at the boundary, right? Because everything is 0 at the boundary, and eventually in the bulk it is like log n. It's like a plateau of size height log n. It's extremely rigid there, and then it sort of gradually goes down to 0. Okay, so which means that it turns out that because of this fact, there's going to be macroscopic contours. If you look at the level curves of this surface, you start from the level 0 at the boundary, and then eventually go to this height c beta log n. So c beta is some particular constant that is actually pretty computable. It's a very explicit function of beta times log n. So you have, for all of these different heights, you have a particular level curve. And as I said, so the Ising model is a bit complicated. The interface is not quite a function, because it can sort of have like detours and like have local bubbles and overhangs. So it turns out, this part is not visible, but it turns out that there are simplified models that people look at, which are known as solid-on-solid models, which are measures just on height functions. So instead of looking at the interface on the 3-dimensional Ising model, you can just look at a function on the 2-dimensional plane, which has some potential. It's like e power minus the summation of the L1 norm of the gradient. And you can sort of convince yourself that sort of the Ising interface should have essentially this sort of an interaction, but except things are somewhat simpler here, because this is actually a legit function. Whereas for the Ising model, the interface can do, at least locally, although they don't affect the macroscopic picture, but it can locally do things like this. So it's not going to be a complete function. So it's going to have like local overhangs and things like that. Although these sizes will be quite small, so if you zoom out, you will not see them. But in terms of actual analysis, it can be quite annoying to do these things. So you can instead of working with this, you can actually work with a function that is actually a bona fide function that actually does look like an actual function, something like this. But you can put the interaction so that it mimics what you expect to be the case in the Ising setting. Okay, so this is the cartoon of what I just said. So this is some hard floor, and then there are multiple levels. So if you now look at it from the top, so you see this level curve. So inside there is a lot of dust, but the white region is all at this given height of c beta log n. And as you sort of zoom in closer to the boundary, you see all these level curves going from c beta log n to 0. Okay, so and this is a macroscopic picture. So so this boundaries will actually be sticking very close to the wall. And so if you look at it from a zoomed out situation where you look at only the hydrodynamic limit, then all of these things become trivial. But you now zoom in, then these interfaces will have non-trivial interaction and fluctuations. So is the picture roughly clear? So for every level, you have some level curve. If you zoom out, they will all be extremely close to the wall. But now if you zoom in, then there is some critical scale at which they fluctuate, and then there is some critical separation. Okay. Okay, so what is the interaction? So far we have seen interactions of the type which were pretty much like non-intersecting random walks or Brownian motions. So here they will certainly be non-intersecting because there are different level curves. They will be like random walk-like, but they will actually have an area tilt factor which was similar to what we saw in the two-dimensional case. So they will be like non-intersecting Brownian motions, but with some area tilted factor. Okay, so and the area tilt is going to be more and more severe as you go down the level. So let's see what I mean by that. Okay, so suppose you're looking at a level k. Okay, so you can look at any level from 0 to, let's say, log n. So you can look at some level k, and now look at the region between the level curve of size at level k and the level k plus 1. So there's going to be some region between the two curves, which is what we care about, right? We want to understand the spacings and whatnot. So every vortex in between this level k curve and the level k plus 1 curve will be at value which is k. So you see that they're all constrained to not hit the floor, right? So if you have a bunch of vortices that are all at level k, of course there are some fluctuations that will make them locally go down, right? Which is so suppose, I mean, this is all still random, right? So when I say something is at level, does not mean that everything is at level k. It means that's a region that is predominantly at level k. Obviously, there are microscopic local fluctuations that can make it go up to k plus 1 or k minus 2. The region is, the larger the chance is of something going down to level 0. And it turns out that if you have a sea of vortices that are all at level k, the most likely way a particular vortex can reach level 0 is by a spike which goes down directly to 0. So you have a sea of k, and then there are downward spikes that can go down to level 0. Now, what is the probability of such a spike? You can so if you think of the Ising interface, so everything here is minus and here it's plus. So in some sense, the cost of such a spike is exponential in the length. So e power minus 4 beta times k. So the probability of a spike of length k is e power minus k. But so that's of course not a very large number. But if the region is very large, if the C of k particles of level k is very large, then there will be some locations at which there is some non-trivial chance of something going down to level 0, because just by chance. So the probability that you stay consistently above the level 0, which you must because of the hard floor constraint, is given by this factor, that at every side you don't have the spike. The probability of having a spike is this probability. So the probability of not having a spike is 1 minus that probability. Yeah, I think this is fine. Yeah. Right. So the probability of having a spike at a particular location is e power minus 4 beta k. And so if you want to respect the hard floor constraint, the probability of that is 1 minus that probability. So probability of not having a spike. And essentially these things are independent across different sites. So raised to the total number of vortices in the C. So which means that you see that this is not a very large, although this is very small and this is somewhat close to 1. If AK is massive, this thing will still become very small. So in some sense, this is sort of saying that as you go closer to the bottom, you cannot have many, many vortices at that height, because that will make it very likely that you will cross the level 0, which is forbidden. And you see that the effect, what is the effect of K? So if you do some basic algebra here, the overall effect is e power minus something. Okay, you don't have to look too closely at that. But the effect of K is geometrically increasing. As K becomes smaller, it's becoming more and more costly to have a lot of vortices at that level. right? Because that should be the right intuition. If you want to avoid level 0, you should try to get up as quickly as possible and stay there. If you spend a lot of time near the floor, there are some chances that you will cross the floor, which is forbidden. That's roughly the intuition. And this consideration shows that the effect that the penalty of being near the floor is geometrically increasing as you get closer to the floor. Okay, so oh yeah. Okay, again, so again, this is some rough heuristic, and then the model that we will study is going to be something where the discrete things are replaced by Brownian motions. And so, as I said, so the interfaces just look like random walks with some area tilt. And Caputo, Yaffe, and Wachtel initiated the study of a natural scaling limit or candidate scaling limit, but the random walks are now replaced by Brownian motions. And so you have some many Brownian motions, let's say. N could be finite or infinite. They're all bigger than 0, so that's the hard constraint. And acting, so these are Brownian motions, non-intersecting, but you have this extra area tilted term. So, and you see that lambda is some parameter which is related to the temperature. So the AI is the area under the ith curve. So between the ith curve and the floor. And the penalty that it faces is e power minus lambda to the I AI, where lambda is some number bigger than 1. So this is sort of encoding the geometric severity as you go closer to the floor. Okay. So you see that, so some of this is the top curve, which does, let's say you can think of this as a 0th curve, which does not face which just faces e power minus area tilt. But as you go closer to the floor, it is sort of forbidding it to have any large area under it, because some of the penalty that it faces is lambda to the I times area. So this is somehow mimicking the situation that I just described. Okay, so right, so this is going to be roughly a model that we'll study, and some of the motivation came from this random interface that I described. Okay, so so these all fall within the sort of realm of Gibbs measures and random curves. So these curves all have this Gibbs property, different Gibbs properties. So what do I mean by that? So all of these random curves have some local resampling invariance property. Okay, so let's see it for the DBM. So remember, for DBM, it was just n Brownian motions conditioned to not intersect each other, right? So now suppose I take these 3 middle curves and erase the part that is marked in red. Okay, so you have this. In this diagram, there are 6 curves. Let's take the middle 3 curves and erase the part between this on this compact domain, and now condition on everything else. So what is the conditional distribution? Because these are n non-intersecting Brownian motions, the conditional distribution will be simply 3 different Brownian bridges between these endpoints that are now conditioned on, respecting the remaining data. What does respecting the remaining data mean? It first of all means that these are non-intersecting, and they also must not intersect the ceiling that is forced by the 2nd curve and the floor forced by the 6th curve. Okay, so that is sort of the local sort of conditional distribution of this measure. And this is what I just said. So is the description clear? So you have n curves, you can erase some compact domain, you can keep everything else, and then given everything else, the conditional distribution is simply like whatever many curves you have deleted, those many non-intersecting Brownian motions, with the further constraint that that they don't hit anything that is not erased. Okay. And in the area tilted setting, again, it's the same, except now the conditional distribution is not just 2 or 3 Brownian bridges conditioned to avoid everything else, but it's 2 or 3 Brownian bridges conditioned to avoid everything else, but also with the area tilted potential. So the conditional distribution is here in this particular example, 2 different Brownian bridges tilted by the e power minus corresponding area factor with the additional non-intersection constraint. Okay. And see, so which means that these things locally somewhat look like Brownian motions, right? So you have some area tilt factor, you have some density, but if you can control them, you get some properties that you can inherit from Brownian motions. And so in particular, there are some important monotonicity properties and regularity estimates that you can inherit from Brownian motion that are crucial in the study of such ensembles. So for example, let's look at these scenarios where you have a system where you condition on the red data, the 2 red points on this side, 2 red points on this side on the red floor. And similarly, you do this with the green data. And let's pretend the situation is such that this green ceiling is above this red ceiling. These green points are above the corresponding red points, and this green floor is also above the red floor. So everything on the right, all the data on the right are ordered in a sense that all of them are bigger than the stuff on the left. Then it turns out that just by non-constitutive properties of Brownian motion, the conditional distribution on the left can be coupled to the conditional distribution on the right, so that the right black stuff, which is the thing that you fill in with, is above the stuff on the left. So if the data on the left is below the data on the right, the conditional distribution on the right is stochastically more than the conditional distribution on the left. Okay, and this is just, in some sense, although you have to be careful about the ceiling and the floor, you can just think of a Brownian bridge. If you take 2 points and a Brownian bridge between them, and 2 other points and a Brownian bridge between them, if the 2 points are raised, the Brownian bridge can be moved up. So the Brownian motion has this natural monotone property, and this is a manifestation of that. Yeah. It turns, yeah, so exactly, I did not, yeah, so this turns out to also hold with the area tilt. Yeah. Yeah, so for both the Gibbs properties that we have discussed, for the non-intersection one and the one with the additional area tilt, this monotonicity is true. And it's actually a very key fact that gets leveraged quite a lot. Okay, so these are local specifications, right? So if I give you everything else, how do you fill in the rest? But you can ask, like, okay, so is there at all an infinite object that satisfies this local specification, right? So this is a primary question that you can ask about a Gibbs measure. If I give you some conditional distributions, can you patch them up to give me an infinite volume measure which has this local specification? And obviously the answer is not always yes, right? Even in this sort of basic setup, like let's say, is there a single infinite curve such that on any finite domain, given everything else, it's a Brownian bridge between connecting the 2 endpoints? So that answer is false, right? So there is no such measure, because you can suppose you can pretend that there was such a curve, which was always like Brownian bridge between any 2 points. Then if you fix the point at -t and fix the point at t, you can draw the Brownian bridge between them, and it can show that regardless of where these 2 points are, the fluctuation at the origin is always going to be like square root t. Suppose there was an infinite curve which had this local specification, then the fluctuation at the origin would be bigger than root t for any t. In particular, that would mean that the value at the origin is not defined. No single measure, there is no measure on a single curve which has this local specification. So obviously, the answer to this question is not always yes, right? Okay, so does that make sense? Okay, so in the special case of DBM, I said, like, there are probabilistic and algebraic properties which are useful. So it turns out that for DBM, the joint density of the locations of the curves are given by some determinantal formulas, and this is known as the Cullen-McGregor formula. And I'll not go too deep into that, but somehow the point is, like, if you want to understand the probability of non-intersection of Brownian motions, it can be sort of encoded in terms of some determinants. So forget this, but let's just look at these 2 Brownian motions between x1 and y1 and x2 and y2. And so it turns out that the probability that if you start a Brownian motion from x1 and x2 and make them end at y1 and y2, the probability that they don't intersect is given by this expression, which is like a determinant. And the reason is the following, that if you do intersect, if the 2 curves do intersect, then you can make some local switching to sort of make the Brownian motion from x1 end up at y2 and vice versa. So you can do some local switchings to transfer the intersection into different endpoints. And this is crucially using the fact that they were both Brownian motions emanating from these 2 points. So in some sense, the 2 properties that are being used are strong Markov property and exchangeability of Brownian motion. So these are both Brownian motions. And okay, so I'm running a bit behind, so I'll skip through this. But just wanted to point out that this determinantal formula does not hold for the area tilted model, because the thing that we used here was this switching, that these are 2 Brownian motions. So once they meet, they both look like Brownian motions from then on. So you can switch whichever way you like, because they're exchangeable. But somehow, if you know that the first curve, the density is 1, and the second curve has this area tilt with factor lambda, third curve has area tilt with factor lambda square, then you cannot do this switching anymore. So the particles are not exchangeable anymore, which means that you don't have this determinantal formula anymore. So this is sort of the source of this non-integrability in this area tilted model, unlike the DBM case where you have access to determinantal formulas. Okay, so I stop at 10:30. Is that? Okay, so just to quickly sort of review some of the developments in DBM. So Corwin and Hammond constructed an edge scaling limit of Dyson-Brownian motion. So Dyson-Brownian motion was growing in time because the variance of the Brownian motion was growing. But now you can do some recentering and scaling to get some sort of infinite family of random curves that are somehow stationary up to this global parabolic shift. So they all look like parabola. They are locally Brownian-like. And it also has the Gibbs property. So the DBM has the Gibbs property and it passes through the limit. And so this is what they termed as the Airy-Line ensemble, which is the stationary process after this global parabolic behavior. The convergence of finite dimensional distribution was considered earlier, and the thing that Corwin and Hammond did was to prove that the measure lives on these non-intersecting paths. And again, the one-point distribution is given by this Tracy-Widom distribution, which is coming from this eigenvalue fluctuations of the matrix. Okay, so let me quickly skip through this. And again, so there's also counterpart for the positive temperature model. So as I said, like, so there was this Brownian last passage percolation, which corresponded to the Dyson-Brownian motion. And then there was this positive temperature polymer model where you looked at a Gibbs measure on the paths and looked at the free energy. And it turns out that you can also get multiple lines out of that, except now they will not be non-intersecting, but they will be roughly non-intersecting in some sense that they will be penalized heavily if they were intersecting. So in some sense, it's a softer version of Airy-Line ensemble. And again, there is some specific explicit form of what the penalty the curves face if they were to cross each other. And the Corwin-Hammond also proved a similar limit in this case. So okay, so at least for the DBM case, there are all these results about convergence to sort of scaling limits. And so one object of interest in such models are tail bounds. So you have some curves, you want to understand their fluctuation behavior. And so it turns out that strong tail bounds often form a key ingredient in the analysis of these curves. And so, as I said, for Airy-Line ensemble, the top line has Tracy-Widom fluctuations. So it's actually very well understood what the fluctuation, what the tail behavior for the Tracy-Widom random variable is. It turns out that the probability that is bigger than theta decays like exponentially in theta to the 3/2. So this is like something slightly fast. This is fatter than the Gaussian, but still like it's a stretch exponential tail. And but even for the Airy-2 process, which is the top line of the Airy-Line ensemble, the one point is the Tracy-Widom distribution, but if you look at multiple points simultaneously, then it's not very clear or it's not very well understood what the joint fluctuation is. And even for the KPC-line ensemble, Ivan, Corwin, and Prometheus here showed similar tail behavior. And it turns out, although they did not get the right constants in certain regimes, but the point is like just using sort of geometric ideas and this line ensemble object, you can get like really sharp tail bounds which matches the sort of optimal constant. And this was done in this joint work with Millen like a year or so back, a couple years now back. So just using this sort of Gibbs property and the global parabolic behavior, you can get sharp tail bounds. Which turn out to be quite useful key inputs in much of the analysis. And again, the arguments are quite geometric, and so they allow also a handle on multi-point bounds that are sometimes quite hard to extract from these determinantal formulas that you have. Okay, so just geometric considerations give you a lot of leverage and a lot of handle on how some of these models behave. And also, just quickly, like how does the curve behave? If I tell you that the height of the curve was high at a particular point, so it turns out that the top curve, if I told you that at the origin it reached height theta, then the value of the top curve, the shape of the top curve, as I said, was typically like a parabola with some fluctuations. Here it becomes like a parabola up to a certain point, and then it becomes this tent type figure, and then continues to be a parabola. And the base of the tent is a function of how high you want the height at the origin to be. Okay, so just quickly, this sort of basically the shape is given by the convex hull of this parabola and this point theta. So typically it's a parabola, you want it to be at height theta, so you take the convex hull and that's the typical shape. And this turns out to be a key starting point in a recent proof of a Brownian scaling limit of geodesic. So I told you, so we have discussed the extremal path, which is a geodesic. And so it's sort of its typical behavior is known. And it was of interest to understand how it behaves if I told you that the length of the geodesic was very large. And it turns out to be a Brownian bridge in that case. And this was one of the key inputs in that analysis. So this was recently done with Milind and Lingfu Zhang, who's a postdoc at Berkeley. And again, you can do such geometric considerations also give you a handle on multi-point distributions, as I said. Okay, so then the question is, okay, so we have somehow addressed the question of existence of these Gibbs measures for the for DBM or such things, but now you can ask about uniqueness. So it is known that area line ensemble is ergodic, and you can ask like whether area line ensemble is the only unique Gibbs measure which has this Brownian Gibbs property, right? So first of all, you have to address existence. One, you have existence, then you have to ask like, is this the only natural candidate? And this was recently resolved in an extensive work by Amol Agarwal and Huang. And essentially, they proved that any infinite line ensemble which is sort of globally parabolic and has the Brownian Gibbs property is the area line ensemble after some random shift. And now if you put in ergodicity, then it becomes the unique one. But the point was the proof here crucially relied on novel Dyson-Brownian motion estimates as well as new monotonicity results. Okay, so the area line ensemble is in some sense a unique line ensemble which is parabolic and has this Brownian Gibbs property where the Gibbs property is just non-intersecting Brownian motions. As I said, so if I go back to the lambda area tilted line ensemble, you lose this integrability. So you don't have this nice DBM estimates that you can make use of in the area case, unless lambda were 1. You see that the whole point of this determinant formula was this Markov chains had to be exchangeable, right? You can do the switching when they meet and things like that. So you see that if lambda were equal to 1, then the area tilt is exactly the same for all of these curves, in which case they become exchangeable. And this does have determinant formulas. And so it turns out that in this particular case where lambda is 1, this line ensemble, the area tilted line ensemble, does converge again to the area line ensemble, which was shown by recently in these 2 papers, Ferrari and Schlossman, who did finite dimensional convergence, and Dimitrov and Serio, who did the process convergence. But remember, for the Ising model, the model of interest was the area tilted model where lambda were not equal to 1. It was strictly bigger than 1. So they have strictly geometric increase. And okay, so you can ask these questions of uniqueness and existence in this setting. So let's start with this finite problem. So where everything is well defined. So you take minus t to t, a domain. You take, let's say, 3 Brownian excursions, condition to not intersect, and with this area tilt factor. So everything is well defined, everything is finite. Now I can ask, okay, so first of all, I should point out that the case n equal to 1, where there's just a single curve, is already well understood, and it was studied in this sort of important work of Ferrari and Schwann, where they showed that if you have one curve with the area tilt and now t goes to infinity, it converges to a stationary process on the line, which is known as this Ferrari-Schwann diffusion. Okay, I'll skip this. And this Ferrari-Schwann diffusion is predicted to be the scaling limit of many one-dimensional interfaces above a hard floor. And in particular, for the two-dimensional Ising example that we talked about, this interface is, you see that this was like a Brownian excursion with some area tilt. So this is like the single curve case. So it was conjectured that this does converge to the Ferrari-Schwann diffusion between the Ising interface. And with Reza Ghezari, who was then a postdoc at Berkeley, we proved some sharp fluctuation bounds for this interface, mimicking the Tracy Widom tails. So the Ferrari-Schwann diffusion does look like, it has a hard floor, so it's not quite like the top line of Ferrari line ensemble, but still in the upper tail regime, it does behave like the Tracy Widom, and we proved like sort of sharp tail bounds. And then subsequently, the full convergence to Ferrari-Schwann was proven in this work by these 4 authors, using what is known as this Ornstein-Zernick theory, which allows one to compare Ising interfaces to random walks. So you can actually think of the Ising interface as a random walk with some area tilt, in which case you can actually then pass to the limit, and the random walk becomes a Brownian motion, and you get the Ferrari-Schwann diffusion. Right. So just to quickly summarize, so the fact that you have a Brownian excursion converging as the domain size grows to infinity is because you have the area tilt. If you just had the Brownian excursion, this would not converge because the fluctuation at the origin will become larger and larger, but the area tilt pulls it down to give you a non-trivial scaling limit. But what about multiple curves is basically what we encountered in the Ising case. So let's say you have now a domain of size t, n non-intersecting curves with the area tilt. Does this have a limit as t and n goes to infinity? T and n go to infinity. And so this paper that initiated the study of this object, CIW, had proven that this is tight. So the area tilt is severe enough so that even if the domain size goes to infinity and the number of curves go to infinity, the object does not blow off to infinity. It stays bounded. So does that statement make sense? Like, so you have Brownian excursions with the area tilt. If you add more and more excursions, it has some competition because they're trying to be non-intersecting, they will try to reach higher values to get some separation. But the area tilt is enough to actually pull it down. So even if you have infinitely many curves, it does not blow off to infinity, is the moral of the story. So which means that you can ask whether there are multiple limit points or there's a unique limit and things like that, because everything is tight. And it turns out that some monotonicity considerations show that if you start from 0 and you take the domain to be larger and you add more and more curves, the line ensemble that you get can only become larger. Like enlarging the domain size and adding more lines makes the line ensemble stochastically more. So in some but still stays tight by the previous result. So you have all these curves that stay tight but are increasing in some sense as you add more and more curves and are enlarging the domain. So this means that they must have a limit by monotonicity, right? So this sequence of distributions, as the domain size and the number of curves become larger and larger, these sequence of measures stochastically increase to some limit, which is termed as the mu0, which is let's say, zero boundary limit of these line ensembles. And so it turns out that it's transition invariant and so on. But this monotonicity is true because you're starting from 0, which is the smallest possible value that the curves can take. But often in cases you are interested in other sort of boundary conditions, like what is known as free boundary conditions, where the curves are starting from some distribution at this point and some distribution at this point, in which case you lose the monotonicity. You don't have that. And you still stay tight if these measures are not too wild, but it's not clear whether you have a unique limit because there is no monotonicity. They're still tight, so you will have limit points, but it was open whether there's a unique limit or not. And if there are multiple limits, what are all the limits? And so in this paper of Amir, Dembo, Yal, Lubeski, and Ofer Zaitouni, they proved that if you fix the number of curves, let's say 4, and send the domain size to infinity, there is a limit. And the limit is the same as if you had 0 boundary condition. So which means that they were very careful in the order in which they took limits. They first took the limit of the domain size to infinity with the fixed curves, and then send the number of curves to infinity to get a uniqueness result. They showed that even if you start from a non-zero boundary condition, if you do it this way, then you will converge again to mu0. So the 0 boundary condition and the free boundary condition have the same limit if you do take the limits in this order. Domain size going to infinity, then number of curves going to infinity. And the proof was very analytical. It relied on this corresponding generator, showing the corresponding generator of the Markov chain is compact and has a positive spectral gap and those kind of things. And in this recent work with Pietro Caputo, we showed that actually, regardless of which order you take limits, you get the same limit point. And it's a straightforward corollary of a more general characterization result. We showed that any uniformly tight line ensemble, which means it does not blow off, which is a consequence of some of the tightness results that were proven earlier, and some technical condition that let's skip over. So any uniformly tight line ensemble with some technical condition must be mu0. So which means that tight line ensembles should only have one limit point, which is mu0, which is given by the 0 boundary condition. And recall that no algebraic inputs were available. So the key ingredients were some a priori strong exponential tail bounds that were obtained using some bootstrapping ideas, not unrelated to the previous tail bound result that I showed, and a coupling that reverses the monotone coupling. So I said Brownian motion has this natural monotone coupling. If the data points are ordered, then the Brownian motions are ordered. It turns out you can also reverse that with some good probability, and that's actually a key step in showing uniqueness. Again, I'll be happy to talk about this more offline, but this is sort of a rough flavor of what the argument is. And yeah, so this is sort of a tail bound. We also showed that for this infinite line ensemble with area tilt, the top line does have Tracy-Widom type tails. And that was a key input in the analysis. Okay, so now you can ask about correlation decay. So you have some infinite object, how fast does the correlation decay? So it turns out that if you have a single line, the Ferrari-Schwann diffusion, it has exponential correlation decay. But for infinitely many lines, we only could show exponential of some polylog, which is less than 1. So this is still this is still not as fast as polynomial. So when you have a single curve, the correlation decays exponentially. When you have infinitely many lines, we don't have such a good control yet. But like we could still give a quantitative rate on how fast the correlation decays. Actually, in an unpublished work with Mriganka, who's my student, and Caputo, we can upgrade this to now a polynomial rate, but it's what the truth is. I believe that it still should be exponential decay, but that seems quite hard to prove. Yeah, so all of this proves that mu0, this zero boundary limit, is the unique transition invariant line ensemble in some sense. But you can ask about non-transition invariant measures. Like what if something is non-transition invariant? And this was not even known for the Ferrari-Spahn. The Ferrari-Spahn is a stationary diffusion, which is transition invariant, obviously. But you can ask, like, is there anything else that is non-transition invariant but has the required Gibbs property, which is that locally it's like a Brownian bridge with the area tilt. And so I'll stop with this. So it turns out that we have now full characterization of all such Gibbs measures. So if you impose non-transition invariance, what happens is this second curve onwards does not get affected too much. It stays still bounded. But the top curve, because it's non-transition invariant, must grow like parabolically, but have some correction. So it turns out that the class of all such measures are parameterized by two values, R and L, which are the corrections from the parabola. So they are like parabolic. The top curve grows parabolically with some linear correction. So on the right, it becomes t square minus r times t, and on the left is t square minus l times t. So there are these two parameter family of non-transition invariant measures. So I think I'm out of time, so I'll sort of stop. Let me see. Yeah, so I mean, some of these are proof ideas, and so I'll stop here. And I'm happy to take questions, and I'm happy to also explain some of the ideas offline if people are interested.
Questions?
Probably you explained it, but that's like, so then how does it compare to this extensive result obtained by Agarwal and Wang?
Yeah, so the difference is in the area case, there is no hard floor, right? So there are infinitely many curves, but like globally parabolic. And so the main sort of effort there is going in sort of controlling the location of the, let's say, the 100th curve. So they want to show that the 100th curve is not too far down. And so they use a lot of DBM estimates to prove that. Here, there is a hard floor. So we know that things cannot go below 0. On the other hand, we don't have DBM estimates. So it's like slightly incomparable in that sense.
Yeah. Okay, that is. Thank you.
Any other questions? I had one question about your mu0. You had some uniqueness sort of thing among all line ensembles. These are line ensembles where you have one top line, or
oh no, it's just like mu0 is all transition invariant measures. Let's say infinitely many lines, all above 0, and have this local Gibbs property. Okay. And also, okay, one has to be a bit careful, because if you take mu0 and then you shift it up by a constant, then it also has the Gibbs property. So you have to rule that out. So you put in some condition that the bottom curves converge to 0.
If there are no other questions, let's thank Shirshendu.